In this lecture, we are going to provide a broad overview of a class of techniques that has come to be called 3D VAR. VAR for variational, 3D essentially tells you we are concerned with problems in the 3-dimensional spatial variable at a given time. So, time is not a factor here. So, the 3D VAR and 4D VAR, VAR always represents variational methods. This is an acronym for variational method. 3D essentially no time, only space. 4D 3 plus 1, 3 for space, 1 plus 1 for time. So, you can think of 3D VAR to be a data assimilation scheme done over the spatial domain at a given time. 4D VAR is a data assimilation scheme that is done as a system evolves in time in the 3-dimensional space. Again, why are we talking about 3, 4 and so on? Most of the all the problems of interest in geophysical sciences happens on and around the earth. So, the space of interest is fundamentally a 3-dimensional space XYZ, and many of the physical processes evolve in time. So, meteorologists in the early days when data assimilation schemes were developed, in order to be able to bring out the distinction between when time is a factor, when time is not a factor, they concocted this notion of 3 and 4. The VAR essentially stems from the fact some of the earliest thought processes that led to the data assimilation scheme arose from the variational approach, which we have indicated when we did forward sensitivity method, 4D VAR method or adjoint method, and that is the door by which these acronyms crept into the vocabulary. So, you understand, my thought is the rose smells the same by whatever name you call. So, you can, if they want to call it 3D VAR, so be. What is the idea? The idea is the underlying idea in 3D data assimilation is always I would like to be able to estimate the unknown true state of a field variable. So, I have a spatial domain, I have a grid embedded in the spatial domain, I have numbered the grid 1 through n. At each of the grid points I have a pressure value or temperature value. At each grid value I am interested in a scalar variable. I am going to collate all the values and create a vector X. In the case of 1D, the grids are along the one dimension. I would like to talk about for a minute. So, in here the grid is like this. In case of 2D, you have the grid. So, in here we have n points along one line. In the case of 2D, I have the x dimension, nx points along the x, ny points along y. So, n is equal to nx times ny. In this example 1, 2, 3, 4, nx is equal to 4, ny is also equal to 4. So, n is equal to 16. In the case of a 3D, I have a grid, I have a grid, I have a grid. So, this is nx, this is ny, this is nz, therefore, n is equal to nx times ny times nz. So, you can see as you go from 1 dimension to 2 dimension to 3 dimension, the size explodes. Let me give you a quick example. Let us assume nx is equal to 100, ny is also equal to 100 and nz is equal to 50. So n is equal to 1, 2, 3, 4, 5. 5 times 10 to the power of 5. That's 500,000. So the whole question is this. So what is the nx? The number of points along the x direction. So let us now consider a spherical coordinate system. So I would like to be able to embed a spherical coordinate system built on the earth. The earth diameter is roughly 8,000 miles. So the circumference of the earth at the equator is roughly 24,000 miles. If you consider a grid of 100 points covering 24,000 miles, the distance between two grid points is 24,000 divided by 100. That is a large distance. 24,000 miles divided by 100. So that is 240 miles. 240. So the distance between two grid points is 240 miles. Now let us take the distance from Bangalore to Madras, for example. It's roughly 200 miles. So there will be one grid point in Madras, one grid point in Bangalore, one grid point in probably Mangalore. Can that accurately capture the variations? No. So if you now change the number, so if you want better accuracy, you have to increase the nx, you have to increase the ny, you have to increase the nz. What is nz? Nz is the number of vertical levels. Generally in meteorology the vertical levels is limited to 50 or 100, that is all. But what is the general problem? For global models, nx, ny, the product of nx and y with nz, the number of points. So that is why in atmospheric sciences, in oceanographic sciences, the value of n quickly in a hurry becomes a million, become tens of millions. So there are two things. One is how to solve conceptually a given problem. Secondly, knowing conceptually how to solve a given problem, how do we solve the problem for which we know that there is an algorithm, but a problem of huge size. Not every conceptual algorithm will be applicable directly to problems of large size. So the curse of dimensionality oftentimes limits what one can do. We have already alluded to these things. So how do we decide what is the value of n? I want to do many things. Whatever I want to do, I must be able to do in my lifetime. Earlier we saw to multiply two matrices of million by million on a machine with a teraflop power, it will take about 12 days to multiply one matrix, to multiply one pair of matrices. Can we afford to solve a problem for 12 days? Can we afford to solve a problem for 1 day? Can we afford to solve a problem in 6 hours? No, we want to be able to make forecasts every 6 hours, every 12 hours, every 24 hours. So what is the time period within which you have to generate forecasts? That provides the time horizon. The computer provides you the computing power. So the time horizon and the computing power together limits the value of n that you can consider in solving problems. So whenever we talk about problems of size n, I want you to keep track of this n. Mathematically I can make this n as large as possible, but physically to be able to put it through the computer there are other limitations. So let us pretend I have a global domain, I have a field variable of interest, I have collated all the field variables of interest in a vector. Vector is of size n. N, if it is a one dimensional problem, two dimensional problem, three dimensional problem, how relates to 1D, 2D, 3D. That is what we have talked about so far. So Rn is called the model space, as we have been talking about all through. Our notation is pretty common through the whole thing. There are two pieces of information about the unknown. One is the background or a prior, and Z is the new observation. Again, this is nothing new, we have talked about it within the Bayesian context at great length. Let me give an example. Suppose you are planning a trip to Paris in the middle of January. You want to be able to pack the right kind of dress. So what did you do? You would like to look at the almanacs that talks about the average low temperature, average high temperature in the middle of January in downtown Paris. And that information is available. This day and age, the almanac is essentially Google, Wikipedia. They all provide you lots of information. How are these information collected? These are summaries over a long time, and that is the information that's called background. The background essentially comes from a summary of the prior information. It's also called climatology. So the background can come from several different directions, from previous knowledge, climatology, previous forecasts, and so on and so forth. So all the gobbledygook mix of everything I know up until this time, if I can spread it over the grid and embed this as a vector, that I call as a background. Z is the new information. RM is called the observation space. Again, we have talked about it at great length in several occasions. The prior so I am going to call XB as the prior, so you can see the Bayesian framework comes into play, sneaks in. The XB has been derived from the previous forecast or the climatology. X is the unknown. X is the unknown I want to be able to estimate. Sorry. X, I'm interested in trying to estimate X or find X. XB is the prior knowledge about X. So X minus XB is X tilde B. X tilde B is called the difference between the unknown and the background. The expected value of XB is 0. The covariance of X tilde B is B. B is a matrix. B is a n by n matrix. So B is a n by n matrix that encapsulates the spatial covariance that underlie the current knowledge of XB. And that should be very clear to us from the previous slide on optimal interpolation as well. What was C there? C was a covariance matrix that is derived from the knowledge of the long time series. So XB. So if you look into Google, you can talk about what is the maximum temperature in downtown Paris noon every day. That is a prediction. So you can, from this data you can compute B by doing simple statistical analysis. So I am assuming I know XB, I know B. What is B? B represents the spatial variability of XB. But when you and I look at Google to go to Paris in the middle of January, we don't worry about the variance. We simply say, hey, the maximum temperature. What did it say? The maximum temperature in downtown Paris in middle of January could be 5 degrees Celsius plus or minus 1. The plus or minus 1 is an indication of XB. 5 degrees is XB. So we have plus or minus gives you the variation. At a given location. I also know the mean value. So I am going to now assume Px is the prior. Prior has the mean XB. The covariance is B. I am going to pretend it is normally distributed. Let us consider that. Let us discuss that for a moment. Normal distribution. What is the beauty of normal distribution? Normal distribution is probably the only distribution, I think it is the only distribution that is uniquely determined by the mean and the variance. So that is a general result in probability theory. Given a density function P of x, given a density function P of x, given a density function P of x, I can compute all the moments What are the moments? First moment, second moment, third moment, central moment, and non-central moments. So what is the expression for the kth moment? The expression for the kth moment is expected value of x to the power k, which is equal to integral, let us assume scalar variable, that is equal to x to the power of k Px dx. I can also consider central moments or centered moment x minus Efx to the power k Pfx dx. I can compute this for every k. So given P, I can compute all moments. Now let's consider the converse. How many moments should I know in order that I can build the probability density function? So given the probability density function, I can compute all moments, simply evaluation of the integral. Some integrals can be evaluated explicitly, some integral, almost all the integrals can be evaluated to a very high degree of approximation numerically. So the passage from distribution to moment, I can do anything. The converse question is a fundamental question. That question has come to be known as moment problem. Moment problem. What is the statement of the moment problem? The moment problem asks the following question: how many moments should I know in order to be able to build the underlying probability density function? There is a very good proof in the first volume of Feller's book that essentially tells you one needs to know infinitely many moments to be able to reconstruct Pfx. So the converse problem of going from moments to distribution is a much tougher problem. So within the context of this moment problem, now I want to mention that normal distribution, Gaussian distribution, is the only unique distribution that is determined by the mean and the variance. Why? If I say x is a Gaussian distribution, x is uniquely decided by the mean and the covariance or the variance. Therefore, in many meteorological application, many statistical application, if I am given a bunch of data, from the data I can grind the mean, from the data I can grind the sample mean and the sample variance, sample covariance. If I have a sample mean and sample covariance, I am going to pretend that underlying random variable is distributed with normally with the sample mean as the mean and the sample covariance as the covariance. So that is the reason why, even though we only know the first moment and second moment, we take liberty, we take a big liberty in assuming that the background is normally distributed with the mean xb and the covariance b. It is a bit of a stretch. All we know is only xb and b. To go from xb and b to the normality with xb as the mean and the b as the covariance is a leap in faith, but we oftentimes do that. So for those of us who would like to look at the specificity of the distribution function, to say Pfx is normal is to say Pfx has this functional form: 1 over 2 pi to the power n by 2. Determinant, so this is the determinant of the matrix B, determinant of the matrix B, exponential of minus jb of x, where jb is given by this quadratic functions. Now please understand, this kind of quadratic functions we have seen several times over and over and over and again. So jb looks like the least square criterion. This jb which looks like the least square criterion comes as an exponent to an exponential function. Look at this now, least square was invented by Gauss. Gaussian distribution is normal. So the least square functional form, trying to describe the functional form of the normal distribution, it is not an accident. It is all invented by the same person. So it is this jb, the mean square type objective function gives rise to the bell shaped curve. So this is the functional form. It is very important to understand this functional form. So this is the information about the background. Now let us go to the observation. Z is the observation. Z is equal to h plus v, h of x plus v. Z contains information about the state. So is the indirect measurements of the state. I am going to assume V is normally distributed. So Z, because of the additivity, because of the uncorrelated nature of X and V, the conditional distribution Px given P of Z given X is given by this distribution, where Jo is given by this. You can see the relation between 5 and 6 and the relation between 8 and 9. So 5 and 6 relates to prior. The background is taken as the prior. So what is the assumption here? The prior information is normally distributed with the known mean and the known covariance. The conditional distribution given X, that means given X, the conditional distribution is given by 8 and 9. So I want you to take a good look at JB in 6 and JO in 5. In particular, I would like to draw attention to the JO in 9. JB, B refers to background, JO, O refers to observation. So Z minus H of X, I am sure you will recall this, Z minus H of X is the residual, this is the residual. So this is essentially least square criterion we have already used. But we did not say anything about least squares, we simply talked about exponent of a underlying normal distribution. So I would like you to develop an appreciation, least squares, normality, they are all intimately associated with each other. We are also, so what are the assumption? XB and V are uncorrelated. XB, what is XB? XB is the background and the observation noise are uncorrelated. These are standard assumptions. Why are these standard assumptions? They are very meaningful. XB and V and 0, V and XB, that means there is no correlation between V and XB. So XBB refers to the prior, ZR refers to the new information. These are two pieces of information about the unknown true state. Please understand, when we did not have prior, we only had observation, we know how to do data simulations for static problem, we use least squares. Now we are going to invoke to the Bayesian type of analysis. I have prior, I have new information. We are going to use PFX, the prior conditional distribution in a Bayes rule to get the posterior distribution, and that is the underlying philosophy of 3D-VAR. So recall the Bayes rule, the posterior, this is the posterior, that is the prior, that is the conditional distribution, P of Z is the normalizing constant. I can now substitute, look at this now, I have expression for PFX, I have expression for conditional distribution, both are normal. I can substitute everything. If I did that, I get this multiplying constant times exponential minus g of x, minus g of x is simply j naught of x plus jb of x, where c is some normalizing constant. We have looked at this kind of a ratio and under normal distribution. We have done several exercises in the chapter on Bayes least squares estimation. So I am trying to do very much similar to what I did in the past. Now what is that I would like to do? I would like to be able to, so now look at this now before I go further. What is this? That is a posterior. You can think of it as a likelihood. Like Fisher. Are you with me? Are you with me, players? So Fisher did not have background, so he only had the conditional distribution. So he considered the notion of likelihood and maximized the likelihood. Here we have posterior. Within the Bayesian context we have already seen the posterior mean is the best estimate. So I would like to be able to minimize appropriate quantities given this setup. That is the optimization problems of interest. So I hope the expression 11 and 12 are very clear. Now 12, what is 12? I want to draw your attention to 12. 12 is simply sum of two quadratic forms, J naught arising from observation, JB arising out of background. So I would like to be able to maximize Px of z with respect to x. We can see Px of z, that means I want to find the location where the Px of z is maximum. When Px of z, please remember Px of z is proportional to, barring a constant, exponential minus j of x, and j of x is equal to j naught of x plus jb of x. So maximizing exponential of minus j of x is equivalent to minimizing j of x. Therefore the algorithm reduces to minimizing this term. This is the background term, this is the observation term. When h of x is equal to linear h of x, both the terms are quadratic. Even h of x is not equal to linear, the first term could be nonlinear, but second term is still quadratic. I am interested in minimizing j of x, which is given in 13. This minimization problem has come to be called the 3D-VAR problem. The 3-dimensional variational simulation problem is essentially minimizing the two quadratic forms, one coming from background, another coming from observation, and so minimize j of x with respect to x is an unconstrained minimization problem, a lot easier, there is no constraint. We can compute the gradient. Gradient of the sum is sum of the gradients. Hessian of the sum is sum of the Hessians. So gradient of j naught, gradient of jb. Substituting summing and equating that to 0, I get the general equation. Now look at this now. The right hand side involves xb, z, b, Jacobian of h, and r, everybody is known. On the left hand side, b is known, r inverse is known, Jacobian of h is known, x I do not know, x I do not know. When h of x is equal to h of x, this reduces to a linear relation which can be solved by any one of the methods. In principle 17 is a nonlinear system, is a nonlinear algebraic system whose solution gives you the optimal analysis. If it is a nonlinear algebraic system, the only way to solve a nonlinear algebraic system is by numerical methods. So there are tons of numerical methods one knows to solve 17. In the special case, I would like to re-emphasize that in the special case when h of x is equal to h of x, so when h of x is equal to h of x, the Jacobian of h is equal to h, everything simplifies. Therefore the matrix like this times x times this matrix, and that is the optimal solution is given by this. This system I have to solve. This system is like Ax is equal to b, again AB is SPD. We already know how to solve SPD systems. And it is no accident that this is exactly the same relation that we derived in the model space formulation in the Bayesian scheme. So this, see the model space formulation, so this is equivalent to Kalman filter equation, so the model space formulation. So what does this tell you? As we will see when we come to Kalman filtering essentially consists of the following step, namely the background is replaced by a forecast, a new observation comes in. How do you combine forecast and the observation? That is the Kalman filter equations. So you can readily see what happens at the filtering stage of the Kalman filter. Kalman filter has multiple stages. One of the stages in Kalman filter is called the filtering phase or a filtering stage. The filtering stage of the Kalman filter is equivalent to 3D-VAR. That is the story. That is the story. And 3D-VAR is very much related to the Bayesian framework, and it is no surprise here we are coming back to Kalman because we have already established the relation between Bayesian least square and linear minimum variance estimate. One did it in the model space, another did in the observational space. We built the bridge between the two using the matrix identity called Sherman-Morrison-Woodbury formula. So now I believe the whole thing is falling in place. Bayesian, linear minimum variance, 3D-VAR, Kalman filter, all these things are all close cousins of each other, and even though the ideas come in different with different labels and different names, and the underlying mathematics are very nearly similar or same. So the equation to this gives you so the equation to 19 gives you the equation to 19 gives you the analysis. The optimal solution for this is called the analysis. So that is called XA analysis. XA is the analysis. Please realize analysis is the fancy term that geophysicists use for the posterior estimate. So what statisticians call as posterior estimate is essentially analysis in geophysical sciences. So we have already seen this. The Hessian of the J function, again I would like you to verify. We have already seen when we did statistical least squares, the inverse of the Hessian is indeed the analysis covariance of the analysis. So I have XA, I have PA. PA is essentially X inverse, that is the Hessian. So this is the analysis covariance. So this is PA analysis covariance. So I have analysis XA from the previous slide given by equation 19. The analysis covariance is given by 12. Why am I interested in analysis covariance? Because we have been talking about statistical methods. In a statistical methods, mean alone will not cut. I need to be able to provide information about the underlying variability as well. So in most of the stochastic predictions, we are not only interested at the level given by the mean, but also we are interested in getting some feel for the underlying covariance. So I have both the mean and the covariance. So this is the best we could do. You gave me the first 2 moments of background and first 2 moments of both the background as well as observation. Now I have combined the first 2 moments of the background of the observation to create the first moment and the second moment of the analysis, the mean of the analysis, the covariance of the analysis. How do I use the covariance of the analysis? Analysis covariance matrix is a matrix. The diagonal elements are all the individual variance. The sum, the trace, the sum of the diagonal elements, which is equal to trace, the total amount of variance across all the components, that provides you a good measure of the quality of the analysis. If that variance is large, you can't put too much faith on your analysis. If that variance is smaller, analysis has a lot more credibility, lot lesser variation. So that is how we would like to be able to, whenever we generate an analysis. What is an analysis? Analysis is a kind of a prediction. What good is a prediction if I do not know how good, what is the degree of variability in my prediction? With respect to lunar eclipse, lunar eclipse and solar eclipse, variability is 0. We know precisely. Can we predict the temperature on noon on March 15th at downtown London? We can't. We can. I can, of course I can generate a number, but what good is that number unless I know what is going to be the underlying variance associated with it. So prediction, deterministic prediction, stochastic prediction. Deterministic prediction, we are content with one number. In stochastic prediction, we also need to have a number that gives you the level, also we need to give the variability. So if you look at current predictions of local weathers, they will say tomorrow there is a chance of 1 inch rain, 80% probability. So 1 inch rain is the measure of the mean level of the rain. 80%. Wow, that's a very high percentage. Very high percentage. So we need to be able to not only give the level but also an associated variance, which is the measure of the variability in my or confidence in my prediction. So in stochastic predictions I need both the mean as well as the variance or the covariance. Once we get this, there is a quick exercise. I can talk about the incremental form of 3D VAR in the model space. So let me run through this very quickly. This is largely related to computational advantages and disadvantages of whichever formulation we want to follow. Let this be the increment. This is called incremental formulation. Substituting this 23 in 20, my J becomes this, that you can readily see, where D is equal to Z minus H of XB. That is what is called the observation increment or the innovation. So we can work with the incremental variable. It can be verified that the optimal increment delta x given by the solution of this. In other words, if I minimize this, the minimizer is given by the solution of this. What is the idea now? The analysis is given by background plus the increment. The increment comes from this analysis. That's another way of looking at it. One of the difficulty in here in solving this is this system as well as the previous system. Let me go back. We need to know B inverse, we need to know R inverse. So that is a question one can ask ourselves. So from a computational point of view, do I know XB and B? Do I know XB and RB inverse? Where B inverse comes in? B inverse comes in as the weight in my objective function, the least squares. So while I know B, my data simulation scheme uses B inverse. B is a very large matrix, n by n is a million. It's the inverse of a million by million matrix. So computationally now one has to ask oneself a question, hey, are we going to really invert these matrices? Is there a way to reformulate the problem without worrying about B inverse but using B only? I hope you appreciate this problem now. We know XB, so what is that we have been given? I know the background information XB and B. I know the observation Z and R, but my J naught uses R inverse. My JB uses B inverse. My JB uses B inverse. B inverse, R inverse, who is going to give you? The theory is beautiful, but you need to be able to compute B inverse, R inverse. Look at this now. The left hand side matrix in here involves these inverses. So where in the world are you going to get these? So the question here is that, is there a way to reformulate? I like the formulation but I don't like the computational demands of it. Is there a way to reformulate it to an equivalent formulation that does not depend on some of the inverses? So that's a question that drives some of these. So look at this now, AM. So I'm going to now call B inverse plus H transpose R inverse H as AM, as AM. B and R are SPD. I am assuming H is a full rank, therefore AM is SPD. If AM is SPD, this combined matrix AM has n eigenvalues. The least of the eigenvalues is positive. The condition number for this matrix is given by lambda 1 by lambda n. Please understand, this is the matrix with which I have to solve AM x is equal to the right hand side. Right hand is the vector. So the quality of the solution depends on the condition number of this matrix AM. The condition number, please recall, lambda 1 by lambda n. While AM could be symmetric and positive definite, since lambda n positive, but lambda n can be very small. So the condition number could be very large since lambda n is positive but small. So lambda n can be small but still positive. So let us assume lambda n as an example is 10 to the power of minus 6. It is still positive but it comes to the denominator, so condition number will be very large. So condition number for SPD matrices becomes very large because the smallest eigenvalue while remaining positive may become very small In those cases I will have headache computationally. So large condition number leads to instabilities in computation. To tame the conditioning we use a suitable transformation called preconditioning. So preconditioning is the methodology by which I am going to get around the challenges posed by an ill conditioned matrix or a matrix with large condition number. What is the matrix of interest here? AM. What is AM? AM is the sum of B inverse plus H transpose R inverse H. These are all mathematical considerations. So how am I going to develop a preconditioning to avoid the challenges of ill conditioned matrices or nearly ill conditioned matrices? That is what we are going to discuss now. So we have assumed B is known, we have assumed R is known. If B is known, let us pretend I know the Cholesky factors G, G transpose. Every SPD has a Cholesky decomposition. So G is also called Cholesky factor or a square root of B. We have already seen that when we did that. So I am now trying to define a new variable U in terms of delta x. You can think of this as a linear transformation or you can think of this as a preconditioning transformation, whichever way you want to call it. So with this delta x is equal to GU, look at this now. If B is equal to GG transpose in 28, B inverse is going to be G minus T G inverse. Minus T means transpose of the inverse. So if I substitute this linear transformation, my JU becomes this. Look at this now. In the first term there is no B, B is gone in the new variable. And what is the minimizer? The minimizer of this is given by this. So I am not trying to show you all the steps. This is the quadratic 30 is a quadratic function. Compute the gradient, equate the gradient to 0, equate it to 0. You get the optimal solution in the new variable U to be given by 31. I hope you keep track of everything. Now what is the matrix AM? AM is given by G transpose H transpose R inverse HG. Now let us look at this matrix IAM. So I have the matrix I. So let us, instead of AM I will consider the matrix A. What is the general result in matrix theory? If lambda is an eigenvalue of A, implies 1 plus lambda is an eigenvalue of I plus A. That's a fact. So if let us assume now if lambda bar 1 is greater than or equal to lambda bar 2 greater than or equal to lambda bar n greater than or equal to 0. So if AM is symmetric positive definite, its eigenvalue, the least eigenvalue is lambda bar n. Please understand, I use lambda 1, lambda 2, lambda 3 for A. I am using lambda bar 1, bar 2, bar n for A bar m. So the eigenvalues, let this be the eigenvalues of this. The eigenvalues of I plus M are 1 plus lambda 1 bar greater than or equal to 1 plus lambda 2 bar greater than or equal to 1 plus lambda n bar, this is greater than 0. Now look at this now, the least eigenvalue is 1 plus lambda n bar. 1 plus lambda n bar can never be close to 0. Lambda n bar is positive, but 1 plus, that means I am bounding the value of the least eigenvalue. That means my condition number is not going to explode in this new space. Therefore I have tamed the condition number by a useful transformation. So such transformations are called preconditioning methods. Preconditioning methods have been known for a long time, that is essentially motivated by to tame the instabilities that may arise because of large or a large condition number ill conditioned cases. So I have already talked about all this. So the condition number for the new matrix is this, and this is always the least eigenvalue is always bounded away from 0 instead of being bounded away from 0. So this matrix is well tamed. If this matrix is well tamed, I should not expect any difficulty in numerical analysis, in numerically trying to compute the solution when I use any method, any meaningful method to solve. So with that we come to the end of the discussion of the so-called 3D-VAR. So in summary, 3D-VAR is another way of looking at the Bayesian formulation, which we have already talked about within the context of statistical estimation theory, especially development of Bayes least squares theory. We are trying to reinforce it by using a new language that is prevalent in atmospheric sciences in data assimilation called 3D-VAR. And we talked about the nature of the solution. We talked about the potential for ill conditioning. We also talked about how do we tame using a preconditioning transformation to be able to induce better conditioning for matrices so that I can have reasonably good stable numerical results. I would like to quickly bring to your attention to the Sherman-Morrison-Woodbury formula. You can see the importance of this formula. Again, I want to tell you something. Sherman-Morrison-Woodbury formula was developed in mathematics for the sake of interest in matrix identity. What is that they were interested in? They were interested in the following. If A is a matrix, if I know A inverse, if I perturb that matrix by adding another matrix, if I am interested in A inverse, can I find the inverse of A plus B, which is the perturbed matrix, simply as a function of A inverse and B? That is the question they were interested in. In other words, if I have a routine to compute A inverse of a matrix, I can plow the entire new matrix A plus B through the algorithm and can compute it. But that is not what they were interested in. I know the inverse of A. A has been updated by B. How do I update A inverse to get the inverse of A plus B? That is the idea. The idea is very similar to what we do in Taylor series. What is the example of in Taylor series? I know the value of the function at f of x. I would like to be able to know the value of the function at f of x plus h. And what do? We simply say this is f of x plus h times f prime of x plus h square divided by 2 times f double prime of x. So what is the idea in general, both here as well as in here? Knowing what I know, how can I extrapolate my knowledge in a neighborhood of around what I know? So I know A inverse from A. A plus B is a matrix which is close to A. So if I know somebody close to somebody who is invertible, can I express my inverse based on the inverse of a fellow whom I know is invertible and I know his inverse? That is the idea. Same thing in here. I know the value of the function at a point x. I am considering neighborhood of a point f of x plus h. How do I extrapolate the value of f of x to f of x plus h? I can do it by knowing the value of the function and its derivative. Here I simply want to be able to use A inverse and B, and that is the beauty of Sherman-Morrison-Woodbury formula. When they developed it, they had no idea whether it will be used at all. They did it for the sake of mathematics, for the sake of beauty. In fact, Sherman-Morrison formula plays such a crucial role in data assimilation, especially in trying to relate the data assimilation formulation from model space to observation space. Why is this relation needed? The model space is n dimensional, observation space is m dimensional. It is seldom m is equal to n. So either m is greater than n or m is less than n. So what is that we would like to take advantage of? It is always cheaper to perform computation in a smaller dimensional space. So n is smaller, you do the operations in model space. If m is smaller, do the operations in the observation space. Who provides this freedom to go between these two worlds? Sherman-Morrison-Woodbury formula. That is beauty. It has no physics, it has no meteorology, it has nothing. It is, yes, a beautiful mathematical enterprise that helps you to build a bridge between these two worlds, and that relieves us of the pain of having to do all the computation only in one world, irrespective of whether m is greater or m is less. It is this power of the Sherman-Morrison-Woodbury formula I would like you to understand, appreciate, and see how repeatedly we have used in our discussion of data assimilation. I would like to make one or two comments. NSEP in the United States, which is called the National Center for Environmental Protection, they use the preconditioned incremental model space for the spectral model. So it's mouthful. Let me tell you this now. What is the model they use? They use spectral model for the phenomenon. What is a spectral model? So consider a primitive equation in a spherical domain. You express the solution in the spherical harmonics as a Fourier series. You substitute the expansion in the spherical domain, in the spherical harmonics, into the differential equation. You reduce a system of partial differential equation to a system of ordinary differential equation on the amplitudes of the spherical harmonics. So what is the expansion of the field variables, such as velocity, such as pressure, such as temperature? So what is that I am assuming? I can encapsulate the spatial variation by involving spherical harmonics. What I don't know, it is amplitude. So we assume the spatial variation can be captured by a clever combination of spherical harmonic functions. Amplitude is something I don't know. So by substituting this Fourier series expansion in spherical domain into the primitive equation model, I can reduce the infinite dimensional partial differential equation to a finite dimensional ODE. The resulting finite dimensional ODEs have come to be called either low order models or spectral models. So spectral models are essentially resulting from the application of the Fourier analysis to the continuous domain. So they consider the spectral model, they do a model space formulation, they use an incremental version. What is incremental version? Delta x. They use the preconditioned incremental model space formulation of the spectral model. I hope you all now appreciate that. That means there is a background. I want to have the analysis. I want to go from prior to posterior. Background is prior, posterior is analysis. I would like to be able to express the analysis, the posterior, as background plus an increment. It is that increment in this incremental formulation that is being computed. That is what we have expressed that. Because of the computational problem, they use the preconditioned version, and they also use model space formulation. So model space formulation of the spectral model, preconditioned increment, as opposed to NSAP, in NASA they use the observation space formulation. So different places develop programs, systems in different formulation because of their belief for the targeted applications in mind. So I would like to leave you with a very interesting computational project. It could be a very nice master's thesis, in fact. Compare. So what is that? You have a 3D VAR problem. I can do an iterative method, Craftsman-like iterative method. I can do a 3D VAR like method. So it behooves us to ask a question to compare the results of 3D VAR with the iterative methods. And also I not only would like you to compare the quality of the result, but also the computational requirements. I think these kinds of projects at the master's level would be very educative, very inspiring, people to be able to look at different kinds of methodologies that could be brought to bear to solve different types of data simulation problems of interest in daily life. Thank you.